So yeah, thank you, James, for a great talk. I'm excited to talk about MIDCA's architectural commitments. So my name is Dustin Dannenhauer. I'm the one who did the introduction, and so I'm currently doing a postdoctoral fellowship at the Naval Research Lab in DC. Yeah, so I wanted to talk about MIDCA's architectural commitments. So we heard from Mike about how MIDCA compares to other cognitive architectures. And sorry, I'm getting a little bit of an echo. I just need to. Okay, I think that's better. Okay, yeah, I think that's good. Okay, I think we fixed the echo. Let me know, Zora, if it still is there in a minute. Okay, so right, MIDCA's architecture. Let's go ahead and get started. So in this talk, so I'm going to talk a little bit about MIDCA's architectural commitments, and I want to try to answer this question: why use MIDCA? So this is a question that I've gotten asked quite a few times over the last few months, and these questions, I think that one of the commitments of MIDCA is metacognition. And so then I'm going to go into some of my work on metacognitive expectations, and I'll talk about some future work. And part of this is to kind of, I don't know if we've really had a conversation about what are MIDCA's architectural commitments. I think that some of them are kind of obvious and clear from the papers, but there might be some other ones that we care about as a community or people working on this project. So if you are someone working on MIDCA so far, you might say, and someone were to ask you, what do you think MIDCA's architectural commitments are? These are some of the things you might say. So you might say that there's an underlying PDDL representation. So PDDL comes from the automated planning community, and has roots even before that with strips and others. And so essentially it's a symbolic representation of a world where you have objects and you have operators that say how you transform a world state from another. So you can have an operator for like picking up objects and how that changes the world state. And just about every MIDCA example has some kind of underlying PDDL representation. So that's kind of consistent throughout. So maybe that's something we want to be committed to making sure we support PDDL. And I have a little asterisk here because we don't have the full PDDL. The other thing is the modular code organization. So that was a decision made by one of the earlier developers, Matt Paisner, and it's consistent throughout. And I really like it, and some other people like it. And so maybe that's something we want to be committed to. Maybe we want to be committed to having a modular structure. The other two are, I feel like, fairly obvious. If you look at some of the research papers, the strict order of phases that cycle. So this is interesting. So we have the perceive, interpret, evaluate, etc. And there's also both cycles, so cognition and metacognition. So those seem like kind of the core commitments. But the other thing, and Mike mentioned this as well in his talk, we should support goal reasoning. So as MIDCA evolves and grows in the future, all possible goal operations and goal reasoning should be able to be possible in the architecture, and the architecture should support that. So now, a little different, answering the question, why should someone use MIDCA? And so this has been, so this is kind of my attempt, and part of this last slide and this slide is to kind of generate some discussion. So any of you who've worked on MIDCA, note down like reasons. And I mean, we heard a few from James, but maybe this is something worth discussing in the discussion section at the end of the workshop. So my attempt is for one, I think it's great for research on metacognition and introspection. So from the ground up, MIDCA is designed to have metacognition as a core functionality. Another thing is that it's written in Python. So Python's really popular, it has a lot of libraries, a lot of software, a lot of AI, data mining, machine learning tools are in Python. So for a lot of people, it's easy to pick up. And then the modular design, I like that. I feel like if I want to add some new components, it's fairly easy. At the bottom here, where I have this little future tag, this is kind of what I envision for the future of MIDCA. So I kind of have this dream where in the future, we can design cognitive agents in MIDCA. And when I say designing a cognitive agent, suppose you have some environment, you have some tasks that you need an agent to do, and you give the agent some knowledge about the world, what actions it can take, what kind of goals it should be executing. And all of that, for the most part, is in the cognitive level, the orange layer. And so because the metacognitive layer is meant to be independent from the world, right? It's just focusing on cognition. Perhaps you can get a lot of metacognitive functionality for free. And this might lead to more robust agents on the person designing the cognitive agent. So that's kind of what I see as a vision. It might be really cool. So potential benefits of metacognition. So this is a table from Mike's PhD thesis, actually. And this just shows some of the causes of reasoning failure. So I wouldn't say this table is exhaustive, but these are just some of the things. And all of these, or just about all of these, have to do with the cognitive level, right? So these are not obstacles or failures in the world. These are things that could go wrong at the cognitive level. And so my work has started before we can even get into dealing with the failures. How do we even know that one of these failures happens? And so, a goal selection failure, goal generation failure, knowledge selection, all of these things, how can we do? So I've started to do some work on metacognitive expectations. So now I'm going to talk about some of the early work I've done. And part of this was done with Hector Munoz-Avila while I was finishing up at Lehigh, and also Mike Cox. So the main idea here is that we can treat cognitive processes like mental actions. So, and this is kind of the idea of drawing an analogy from planning actions and world states to mental actions and mental states. And a mental action is something that transforms one mental state to another one. So what is a mental state? So in MIDCA, right, so we so far, and Mike mentioned this, that MIDCA's memory is kind of weak. So for now, we kind of have a dictionary with certain kinds of variables that store data in memory. So a mental state for this purposes is a collection of variables. And we have a variable for the following. So selected goals, pending goals. And so we get this vector of length 7. Now, a mental action essentially performs reads or updates to the memory, and a mental state is like a snapshot of the memory. So before planning is done, before planning for a goal for the first time, in the agent's memory, it might not have any plan, but it might have a goal and a world state. And so that's the prior state. And then afterwards, it generates a plan, and now that's stored in memory, and that would be the post-mental state. And so some of MIDCA's phases have just a single module. So for some of these, they're just single mental action. But really, the focus of this slide is just to emphasize that mental actions are at the module level, because interpret, which performs the first 3 steps of the goal-driven autonomy process, where you detect discrepancies, explain them, and possibly formulate and insert new goals, that all happens in interpret. And so each one of these can be whole areas of research, and so each one of these should be its own mental action. I don't think it would make sense to consider all 3 of them together as a single mental. I think you care about reasoning at a finer granularity. So mental states are obtained through a cognitive trace, and so this happens in the monitor phase. And so this is an example of the intend phase, or rather the module inside the intend phase, which is just doing goal selection. So in this case, PG stands for, on the right here, stands for pending goals. And so there are 3 goals related to blocks in a blocks world domain. And SG means selected goals. And so what happens is, in this horizontal line here, this is where the mental action intend occurs. And so what we see is that in this case, all 3 goals have been selected for the agent to pursue. And then the next phase is plan. And the module in the plan phase, which is going to perform planning, has a world variable and a selected goals, and the mental state after is actually showing an empty plan. So this is actually what it might look like if we have a problem. We would expect this to be a plan with 1 or more actions that the agent's planning to execute. So just to show in the diagram where these fit in, the metacognitive expectations are in the interpret phase, and the trace is gathered in the monitor phase. So when I say a metacognitive expectation, what am I talking about? So essentially a function, this is what we have so far, and I think that moving forward, this will evolve and we'll have richer types of these, but even just this alone can be powerful. So we have a prior mental state, which is like a snapshot of the memory, a post-mental state, and a mental action. And essentially, the expectation holds or it doesn't hold. So it's either true or false. Example, when the agent generates a discrepancy, then the agent will generate an explanation for this discrepancy. In other words, if something surprising happens, the agent will be able to explain it. So if an agent can't explain why something unusual happened, that might be a problem where metacognition steps in. So this is how we would define it. These are, so if you remember before when I was talking about the mental states having a vector of length 7, these are two of the values in that vector. One is the discrepancies and one is the explanation. So at the bottom here, when the discrepancies is not null, when there's some discrepancy, we expect explanations to not be null either. And so the cool thing is that this is totally agnostic of whatever domain you're operating in. It doesn't care about the world. You could be flying a plane, drive, I don't know how you maneuver a sub, but maneuvering a sub, whatever that verb is, or driving a car, and this is an expectation, and this is a meta expectation. So we've done some experiments, and so this experiment is in the NBeacons domain, essentially a modified version of Mars World, which is something from some earlier work. Basically, it's a 10 by 10 grid, and there is an agent in the middle, and there are these beacons, which are numbered 0 to 9, and the agent is given goals to navigate to a beacon and activate it, and pits that it must avoid. This domain, and then the next domain I'll talk about, are fully observable. So the agent can see this, and so in the beginning, the agent will just avoid sandpits, no problem. But unknown to the agent and the agent designer, there is wind. So after some time, their wind starts blowing, and it has a permanent effect on the agent's actions. So whenever, think of wind as a kind of permanent change to the environment. I know wind in real life generally can change very quickly, but this is just kind of an example for this kind of behavior where domains change over time. So what happens with wind is that once the wind starts blowing after a certain amount of time, for the rest of the time, the agent, when it moves in the direction of the wind, so suppose the wind is moving east and the agent moves east, it will be blown an extra 3 or 4 tiles. And now the agent might find itself stuck in a sand pit. And so basically some of the planning domain knowledge could become outdated. So we implemented 3 kinds of agents. We did an ablation study. The first kind of agent, and so the last agent has these metacognitive expectations that I was just talking about. Specifically, it has the explanation expectation. So the first agent is a replanning agent. It doesn't do any discrepancy detection. So basically, goals are given to it. It generates a plan. It starts executing it. If it gets stuck in a sandpit, it just keeps trying to move where it thinks it's going to go until it's done executing the plan, and then it just tries the next goal. So it gets stuck easily, basically. Once the wind starts blowing, it's blown into a sandpit. Now we have a GDA agent, and this performs discrepancy detection at the cognitive level. So immediately know after executing an action where it gets blown and stuck in the sand, it'll perform an explanation that it's stuck, and then it will change its goal to become unstuck. And to become unstuck, it has to execute 5 push actions to free itself. So what happens is that the GD agent gets stuck easily, but it responds much faster. It doesn't try to execute a bunch of unnecessary actions before switching goals. Finally, the metacognitive agent has this, so it's has the same functionality as the GDA, but it also has metacognitive expectation. And in this work, we assume kind of an oracle function that knows how to update the planning operator. That's certainly an area for future work. But if we assume that we have that, because this work is focused on the expectations, how can we detect when we're in situations where we want to trigger metacognitive functionality? So essentially what happens is the meta expectation for explanation gets triggered, because what happens is that the agent gets blown and the agent can't generate an explanation for why it's been shifted. It only knows that it's stuck. And so it's able to update its domain knowledge because this metacognition triggers. So what we see is that we actually get a lower execution cost per goal achieved. So the replanning agent takes, so the y-axis here is execution cost, which is measured in number of actions executed. The bottom is the number of goals achieved. And so at the very beginning, they're all equivalent because there's no wind. And then what happens is that wind starts blowing, the replanning agent gets stuck, and then it's taking a lot of time because it's executing the rest of its plan, and then it's like, oh, I'm stuck. The GDA agent responds faster. The agent with the metacognitive expectations, it actually will update its planning operator so that it knows when it's going to move east, the wind is going to blow it, and it starts avoiding the sand pits after that. So this is one situation where in domains change over time, there's a benefit. And we did another experiment in another domain that has a similar property. So it has kind of a permanent change over time. We call this aggressive arsonist. So just for the sake of time, I might not go into as much detail, but happy to take questions or feel free to ask me later. This is based on the arsonist domain from Paisner and others from 2014. Essentially, it's the blocks world domain where blocks can be lit on fire. But in this one, after a certain amount of time, the arsonist just gets fed up. His fires keep getting put out, and he's like, you know what? I got to step up my game. So he uses a stronger fuel, and when he lights his fires, 2 blocks get lit on fire. And if the agent tries to put out the top fire, nothing happens because the bottom fire keeps it burning. So the fire is like burning up. So the only way to put out a fire once the arsonist becomes aggressive is to put out the bottom block. So if the agent doesn't learn that, and so in this we actually see stronger failure. So both replanning and GDA get to a point where all the blocks are on fire. And in this case, fire is a problem because the agent cannot pick up a block if it's on fire. And what's interesting here is that actually the GDA agent seems to achieve a little bit less goals, and that's partly because it responds quicker and it almost gets stuck quicker. So I'm just about ready to wrap up, and I just want to note this vision for MIDCA's future. So these metacognitive, so I've shown one metacognitive expectation for an explanation module, and so I think there are other kinds of meta expectations for other ones, but the ones I've talked about so far are they're domain independent, which is great. So we showed the benefit in 2 domains, but they're still module dependent, right? So this is still specific to explanation. And we might have another example where we always expect our planning component can generate a plan, right? So I would say if I can't generate a plan to achieve a goal, maybe that's a cognitive level problem. But having an expectation like the one I just described, that's also module dependent. And so what I think is a really interesting area for future work is, could we learn meta expectations? And so this kind of goes back to that vision in the future where if we could have someone who designs a cognitive agent, they might add their own modules, right? So James, in his previous talk, he added some rebellion modules. How could we have meta expectations for custom modules? Is that even possible? What would that look like? Perhaps we could learn them. And so just summarizing what I've talked about, metacognition is one of the core architectural commitments for MIDCA. I would like us all to think about, what do we think the architectural commitment should be? And so I showed some results in 2 domains for a metacognitive expectation for explanation. And for future work, could we learn meta expectations and also just building more metacognitive capabilities? So thank you.